In this video, we're going to see an example of how we can use the monotone convergence theorem to evaluate limits. If you remember, the monotone convergence theorem tells us that if a sequence is monotone and bounded, then it is convergent. So the theorem is really just telling us that the limit exists, but it's not really telling us how to actually compute the limit. But you see, when you're given a sequence, sometimes even knowing whether the limit exists or not is very difficult. So, well, maybe we can check instead whether the sequence is monotone and bounded, and if we check those boxes, right, if we know that it's monotone and it's bounded, then I know that the limit exists. And that's already a huge gain. I know that at least I have a hope of finding a limit. And then after that, we'll use some tricks that will allow us to actually compute the limit. This is in particular very powerful when we have sequences that are defined recursively, as we're going to see next. Okay, so we have this exercise that is asking us to find the limit of the sequence is given by the first term is equal to 1, and then we're going to define each term an plus 1 as 3 minus 1 over an. Okay, so we take the next one is going to be 3 minus 1 over n, so over an, so like 1 over the previous term in the sequence. Okay, how on earth I compute this limit? I don't really know, because I cannot use limit laws. There's nothing like really know. But well, let's see. Could this be increasing or decreasing, or is it bounded? Let's try to ask ourselves questions. So, it seems that, well, I have 3 minus 1 over n, so could it be going up? Could it be going down? I don't know. But we could explore some values and see. I invite you to do that. But if you want to just continue watching, let's do that. We're going to show that the sequence is increasing and bounded above. So I'm going to first show that it's increasing, then I'm going to show that it's bounded above, and then we're going to use the monotone convergence theorem to conclude that the sequence has a limit. Okay. How do I prove that this thing is increasing? Well, you see, it's something about like ANs for all n. We have to show that an is less than or equal to an plus 1 for all n in the natural numbers. It feels to me like induction could be a good strategy, and that's what I'm going to do. We're going to use induction. So what is the base case? Well, we need to show then that a1 is less than or equal to a2. Well, a1 is equal to 1 and a2 is equal to 2. So yeah, a1 is less than or equal to 2. Great. Now, for the inductive step, we're going to assume this is true for n. So we're going to assume that an is less than or equal to an plus 1. Okay. That would imply that then 1 over an plus 1 is less than or equal to 1 over an. And then, well, we have that an plus 2, which is 3 minus 1 over an plus 1, is less than or equal to 3 minus 1 over an. But that is an plus 1, which is exactly what we wanted to prove. So by induction, this is true for all n's, so indeed my sequence is increasing. Okay, now I have to show that my sequence is bounded above. Well, what do we need to show? We need to show that an is less than some bound, and here you see is 3 minus something, so my feeling is that 3 is a good candidate for an upper bound. It doesn't have to be the supremum, it just needs a good candidate, right? So 3 sounds like good because we'll have 3 minus something that I think is going to be positive all the time, which makes sense to assume. So okay, let's see if this is true. Again, induction feels like a right strategy. So what is the base case? Well, a1 is equal to 1, which is obviously less than 3. Now we're going to assume that this is true for n, so we're going to assume that an is less than 3, and we need to show that an plus 1 is less than 3. Okay, so if an is less than 3, then we know that 1 over an is bigger than 1 over 3. But now we have a negative sign, so minus 1 over an is less than minus 1 over 3. But then add 3 sides and we end up with 3 minus 1 over an is less than 3 minus 1 over 3. Okay, But 3 minus something positive is, well, less than 3. And the thing here we have on the left in the last inequality, that is an plus 1. So indeed, an plus 1 is less than 3. So indeed, we can conclude by induction that an is strictly less than 3 for all natural numbers. Very good. So we know that my sequence is increasing and bounded above, so it converges. Very good. Right, so the monotone convergence theorem, it tells me that it has a limit, but it doesn't tell me what the limit is. That's a bit annoying, but okay, at least I know it exists. So we know that the limit is equal to L for some L. We just need to find what L is. That's my only problem. Well, here's an idea. We're going to use this recurrence relation. And to do that, I want you to convince yourself that the limit as n approaches infinity of an plus 1 is the same as the limit of an. If you look at it, this makes sense. What is the sequence an plus 1? It's the same thing as the sequence of the an's, except that we removed the first term. We just looked at it, we took the first term, we threw it away, and we ended up with a new sequence. But the behavior is pretty much the same. The only thing that changes is that, well, the first term of my original sequence is no longer there. So try to convince yourself that this is true. Now, if this is true, we can use the limit laws here. Because you see, the limit of an plus 1 is the limit of 3 minus 1 over an. But then using all the limit laws, because now I am allowed to use the limit laws because I know that the limit of an exists. So this is just 3 minus 1 over the limit of an. Oh, but then we said that the limit of an plus 1 and the limit of an were both the same. I call it L. So we end up with this equation. We end up with L is equal to 3 minus 1 over L. Now let's massage this expression a little bit. And we obtain this equation here, L squared minus 3L plus 1 equals 0. This is something that we know how to solve pretty well. It tells me that L is, well, 3 plus minus square root of 5 over 2. Okay, very good. But we have two options, and the limit is unique, so we should pick only one. Which one should it be? Well, the first one, the one of 3 plus square root of 5 over 2 is greater than 1. You can check. 3 is bigger than 2. 3 plus square root of 5 bigger than 2, definitely, so this is bigger than 1. It's actually bigger than 2. And the other one, if you check, this is less than 1. It's like 3 minus square root of 5 over 2 is like 0.38 something. It's definitely less than 1. Then which one would make sense? Well, we have to take a look at my sequence and see what happens. Well, the sequence is increasing, and I know that the first term was equal to 1. That means that all my terms are bigger than or equal to 1. Correct? Well, if all my terms are bigger than or equal to 1, can I get as close as I would like to a number that is strictly less than 1? There is no hope for that, right? Like if you are all living above here, right? And how can you get close to something like below? It is absolutely impossible. So then my limit has to be the first option. The limit is 3 plus square root of 5 over 2. And that completes our proof.